So, for question 5, you're given two position vectors. Now you can write your position vector as the vector OA, which is position vector for A from some fixed origin, which is 5i plus 4j, and the position vector for B, again from some fixed origin, so the vector OB is minus 2i minus 3j. Now you can represent those graphically, both from the same fixed origin. You've got the vector OA here, plus 5i plus 4j, and OB here, minus 2i and minus 3j. So part A wants the vector AB. So this vector here. Now, what we've got to think is we need to create ourselves a path. We want to start from the point A and then eventually reach point B, but we don't have the information for the direct path. But we can go from A to O, and then we can add on the path from O to B. Now we do have information about that. Now the vector OB, fine, we've got what that is. We don't have quite the vector AO, but all that means is if we're going from A to O, it's the same vector just with negatives in each direction. So we can really write that as minus OA plus OB. So if we substitute in our vectors now, with the minus we have minus 5i minus 4j plus minus 2i minus 3j from the vector OB. So if we can combine our i's now, minus 5i minus 2j, which is minus 7i, minus 4j plus minus 3j is minus 7j. Okay, and that would be our vector for AB. Alternatively, you can display this as a column vector, which would be minus 7, that's fine. If you use column vectors throughout, that's also fine, unless it specifically says use I or J notation, okay, but that would be the column vector notation. So then we've got the modulus of this vector. Well, all the modulus means, or the magnitude, is that we are going to use Pythagoras. So we're going to take our values, and we're going to take the square root of minus 7 squared plus minus 7 squared. So 49 plus 49, 98. And it does say it as a simplified surd, so you need to make sure that you simplify, but your calculator will do this for you, which is 7 root 2. And that'll be your final answer for 5. Moving on to 6 then. The key expression, they give you a load of text, fine, you've got to be able to work it out, but it specifically says that you're going to use a linear model. Now, if it's a linear model, you know what the general form of a linear expression is. The general form is y equals mx plus c, where x and y are your two variables there. So, using the new notation then, we can substitute in. And the thing that we are changing, we are looking at the time changing, so we are changing the time, which is our x, and the thing that's then going to change as a result of that is our height of our tree, so the h must be the y. So in other words, the general form for this particular problem is h is equal to mt plus c. Now, we can't use that though, because we don't know what the values for m and c are, but we are given some extra information which we can then use to find those. And because there are two unknowns, we need at least two sets of information to be able to solve this, which fortunately they give us, two separate lines. They nicely lay it out. So the first line says that after 3 years, the height is 2.35 meters. So all we need to do is substitute that into our expression and say, therefore, that's telling us that our height, 2.35, is equal to m times our year, which is 3, so 3m plus c. And then the second line, exactly the same again, our height, 3.28, is equal to our time, which is 6, so 6m plus c. Let's call that equation 1 and equation 2. And all you've got there is just a pair of simultaneous equations. Now, the easiest way to do this is, because they both got a singular c, is to just subtract the two equations. Now you can do 1 take away 2, but actually for our case I'm going to do 2 minus 1 just because it's a little bit easier, because the second equation's got larger numbers. So 3.28 take away 2.35 is 0.93 is equal to 3m plus c. Oh, sorry. We've just got rid of the c, sorry, no plus c, so is equal to 3m. So m is equal to 0.31. So that's our value for m. We now need to substitute this in to get a value for c. Doesn't matter which equation you use, but you can use the other one to check it. If I take the top one, for example, 2.35, 3m, well, as we know, is 0.93 plus c. C is 1.42. So our equation then is, well, the height is variable, so h is equal to, our m is fixed, so 0.31. T is the number of years, so that's changing, and our c is fixed, 1.42. And that's our equation. We've then got the last little bit, which says that the height when planted is 140 centimetres. Does our model, as we've worked out in part A, fit? Well, we've got to think, if we're looking at the planted time, planted means our t value is equal to 0. Okay, so the time of planting, t is equal to 0. Well, if we substitute that in from our model, that gets us a height of 1.42 metres. And remember, this particular calculation, we calculated it all in metres. So that is our initial height from the model. Now, they're saying that the actual height was approximately 140 centimetres. As 140 centimetres, let's just convert it, is equal to 1.4 metres. And 1.4 metres is approximately equal to the model's value of 1.42 metres. So because those values are very close, this implies our model fits the data, or something along those lines. But basically, you need to state what the important quantity in this equation is, which is this 1.42, which is our initial height when it's planted. Make sure you state what that is, and then it's about comparing it to this value. So if the value is very close, then chances are your model is probably a pretty good model. If the value is very different, then your model obviously doesn't work. But it doesn't mean that this is invalid, it just means that you would have to apply a different model.